Okay. So let's see, let's remember where we are, because it's been a little while since I last lectured. We had an excellent lecture from Natalie on Wednesday that's actually topical because it reminds us of swap regret. Okay, cool. So first of all, swap regret. Let's remember swap regret, because we've seen it a couple of times in this class. Okay, so first of all, this is a guarantee in sort of this standard online expert setting where you've got some set of K actions. Every day you need to choose an action, and then you learn the cost or the gain of the action you chose. And what's different when it comes to swap regret compared to external regret, the sort of standard benchmark we've been talking about through most of the class, is what benchmark you compare yourselves to. In the swap regret setting, the benchmark you compare yourselves to isn't just fixed actions, but is some more complicated transformation of the actual sequence of actions that has been played. Okay, so for external regret, you sort of transform that sequence just into a fixed action that you play the whole time. But for swap regret, you can find an element in the benchmark class by applying any swap rule, which can map actions of any sort to actions of any sort. Okay, and so the more complicated a sequence of actions you've played, the richer your benchmark class. Okay, now, the first time we encountered this, we sort of derived an algorithm for it of sort of a classical sort that solves a minimax problem every round, but like when we sort of pulled on the string and actually like derived the closed form algorithm for swap regret, it was sort of solving some kind of fixed point problem. It was computing the top eigenvector for a matrix. This is sort of typical of algorithms for solving this problem. And it sort of made, like I claimed at the time at least that it sort of made sense that it was solving like a fixed point problem, because swap regret is a form of subsequence regret that is self-referential. It asks for no regret on the subsequence of rounds for which you played some particular action. Okay, so you have some self-referential thing, it makes sense you solve for some fixed point problem. Okay, now as Natalie showed us last week, that's not the only way to get no swap regret, but let's remember what the two kinds of bounds were. So from these sort of fixed point algorithms, the kinds of bounds we got on swap regret were on the order of square root of k, the number of experts, over square root of t. Okay, compare this to the bounds we got for external regret, which were like log k, or square root of log k over root t. Okay, so in some sense, the swap regret bounds were like exponentially worse in k, the number of experts. Now, what Natalie derived last class from these sort of two recent papers is that there was a way to get swap regret that depended only logarithmically on the number of actions. Okay, so sort of matching these external regret algorithms without solving for a fixed point. But that came with a pretty severe cost, which was that although the dependence on the number of actions was improved exponentially, the dependence on the time horizon was made worse exponentially. Okay, so rather than sort of a bound that sort of went to zero, rather than a bound that went to zero sort of at a rate of 1 over root t, you got a bound that went to zero more slowly than 1 over log t. Okay, so that was the cost. Okay, now tying swap regret back to the stream we've been talking about recently, I'm going to focus once more on this regime where the thing we will care about most is the dependence on t. So I'm going to talk about, optimal swap regret bounds. And by that, I'm referring to sort of the 1 over root t dependence rather than the log k dependence. Okay, so like, by the way, like the sort of bounds we derived of the form, root k over root t, those are known to be optimal, again, from these sort of new papers in the regime where you want a 1 over root t dependence. Okay, so like you can't get the best of both worlds. If you want a log k dependence, you need to suffer this sort of exponential factor in t. Okay, but just when I say sort of optimal swap regret bounds, I mean, I'm talking about t. So I'm talking about aiming for this 1 over root t. Okay, so let's remember now where we are in this stream of making predictions for action. Predictions so that various downstream decision makers can decide whether or not to, or can use our predictions to take actions and hopefully have regret guarantees of various sorts. Okay, so our intellectual development of this came in a couple of stages. First, we said, okay, suppose we want our downstream decision makers to just have no external regret. Okay. Then it was pretty easy, actually, to make predictions so that every downstream decision maker would have no external regret at the optimal rate, at root t. With sort of a root t rate, it was just sort of like report the empirical history of what's happened so far with noise. And the analysis was an elaboration of the claim that we have just tricked everyone into playing follow the perturbed leader, which is a no regret algorithm. Then we studied calibration. Okay, calibrated forecasts had the amazing property that, again, for every downstream decision maker, actually, like, best responding to the forecasts was, up to regret terms that we'll talk about in a moment, sort of a dominant strategy amongst all policies. Okay, you had no regret to any other policy mapping forecasts to actions. And in particular, this was stronger than no swap regret, because no swap regret is having no regret to sort of strategy modification rules that map your actions to actions. But of course, your actions are a function of the forecast if you're best responding to them. So having no regret to policies that map forecast to actions, that's a stronger benchmark class than having no regret to swap modification rules that map your actions to actions. Okay, so that was great. We like, for every downstream decision maker, now we had a way of causing their best responses to have no swap regret. Okay, but it wasn't at the optimal rate. Okay, like, even in one dimension, the best bounds we got were like t to the 3/4, and I claimed that if you worked a little harder, you get t to the 2/3, but not root t, and that was just in one dimension. And our bounds got sort of exponentially worse in d as the dimension got bigger. We got bounds that were sort of like t to the d over d plus 1, so becoming sort of in high dimensional spaces like just barely sublinear. Okay, so this was a way to get every downstream decision maker to have, no swap regret, but maybe by like an abuse of the word no. Like it was, in principle, like sublinear swap regret, but like just barely. Okay, so in some sense, like qualitatively, better than this sort of simple perturbation algorithm, because we cause downstream decision makers to have no swap regret rather than no external regret, but quantitatively much worse. Okay. Okay, and then we developed sort of a piece of abstract machinery that I claimed would be helpful, but that we haven't like put to good use yet, which is just a way to make predictions of the payoff relevant state that are unbiased, conditional on a polynomial number of events. Okay, we gave, it was sort of solving the following problem. You give me a collection of conditioning events. These are just like functions that evaluate to like 0 or 1, say, as a function of the history, as a function of any external context, and importantly, as a function of the prediction that I make. Okay, and the promise was that so long as you can evaluate these in polynomial time, you can evaluate these events, you know when they happen or not, then there's a prediction algorithm that at every round makes spends an amount of computation that scales polynomially with the dimension, okay, not with the number of forecasts in the dimension, which is like 2 to the d, but just polynomial with d, and polynomially with the number of conditioning events, and produces a sequence of forecasts such that even in an adversarial setting, if we look back at any of these conditioning events, so the subsequence of rounds for which these conditioning events were active, and we look at any coordinate of our predictions, the bias in that coordinate, meaning the difference between the sum of the prediction in that coordinate and the sum of the outcome in that coordinate, the absolute value of that, the bias in that coordinate scaled only with root t times some log terms, log in the dimension and log in the number of conditioning events. Okay, so long as the number of conditioning events was like polynomial in D, say, we were looking at bounds that were like root t log D, something like that. Okay, so right, so the point was, calibration, we don't have efficient algorithms for, but it wasn't like we've sort of pinned our finger on partly at least the reason for that. It was not because in the calibration game there's an exponential number of forecasts you could make. It wasn't because we're solving a zero-sum game that has exponentially many actions. That's also true of this unbiased prediction game, and there we have polynomial time algorithms. It was because we were asking for sort of low bias subject to exponentially many conditioning events. Okay, what we sort of showed was that if there's only polynomially many conditioning events, not only can you do it computationally efficiently, you can sort of do it at these optimal root t rates. Okay, so this is some, like some tool we have now, but we haven't used it yet. And what I want to start by doing now is sort of saying, okay, we have this tool at our disposal. We can define arbitrary polynomial collection of events and make predictions that are unbiased subject to those events. Suppose I've got a collection of maybe polynomially many downstream decision makers that I have in mind. Okay, so I know what their utility functions are. There's polynomially many of them. How can I make forecasts targeted at those decision makers using this toolkit we've developed so that when those decision makers best respond to our forecasts, they have diminishing swap regret. So qualitatively, the same thing we get from calibration, but hopefully at sort of optimal rates that sort of depend with root t, that sort of scale with root t and don't have any terrible scaling behavior with d. So we want to be able to do this in high dimension. Okay, so that's the goal. All right, so that was sort of the summary of where we've been and reminding us of swap regret. Yeah. Okay, good. So this is one thing that's going to be qualitatively not. So we're going to give stronger quantitative bounds than we were able to get from calibration. So instead of getting downstream decision makers to have regret scaling like t to the d over d plus 1, it's going to be like root t. That's the quantitative gain. But there will be an important qualitative weakness compared to calibration, which is calibration gave us this guarantee simultaneously for every possible downstream decision maker. You've put your finger on something I've said, which is going to be weaker than this. We're not gonna make these forecasts that are going to be good for all possible downstream decision makers. You tell me some polynomial number of decision makers you care about, meaning you tell me their utility functions, and I will efficiently make predictions that are good for them. But if I wanted to handle all possible downstream decision makers, I would again run into the kinds of problems I have with calibration, because I would again have lots and lots of conditioning events.
To follow up on that, is this sort of a Titan possibility? Like, if you work does that exactly require that you also be calibrated?
That's a good question. I don't think it does. So there's an interesting thing to put your finger on there. Well, I mean, maybe you're sort of looking ahead to applications of this, but like the way we're going to analyze it, there's no, we're going to look at a single downstream decision maker and an adversarially chosen sequence of states and show that if we are unbiased subject to a collection of events defined in terms of that decision maker, then they have low swap regret. And the place where sort of like basically there will be a polynomial collection of events that are necessary to give this guarantee for a particular decision maker, and if we care about multiple decision makers, we can be unbiased, subject to the events that are relevant for each of them. And so long as there are only polynomially many decision makers, we can do it efficiently, simultaneously for all of them. But no part of the analysis will depend on somehow in some game theoretic setting, coordinating their actions. Although you're right that one application of this kind of thing is that, if I know that people are playing in a game that, and maybe I know that there's each person has some utility function from some polynomial collection of utility functions. Maybe there's a low dimensional type space, say. Then one application of this is I can make these predictions. People can best respond to them, and since they will all have no swap regret, we know from previous things we've shown in this course that their empirical play will converge to correlated equilibrium. That's right. So like just as with calibration, one use case of the kind of technology I'm going to be talking about is publishing a signal that coordinates some population to play a correlated equilibrium.
I guess it now makes sense. That you can get all the way down to log PO for that specific application versus one of the primary points.
Yeah, so you're saying like there's these like optimistic algorithms, and if I know that I'm playing one of these optimistic algorithms against other players who are also doing the same, then I can get regret scaling more like 1/t instead of 1/√t. Yeah, so I guess you could ask that question: is it possible to get those kinds of rates with sort of a setting like this, where there's a centralized coordinator who's publishing a signal that everyone is best responding to, rather than having them run their own algorithms? I guess it would need a different analysis, because it is not possible against an adversary to get swap regret better than 1/√t. And what we're going to show is that for the kinds of forecasts we're going to publish, you get 1/√t regret against an adversary. It's not possible to improve that to 1/t. But yeah, once you specialize to playing a particular game, then in principle we know how to get better rates with particular algorithms. And you could ask, can you get those same rates with unsophisticated players who are just best responding to a forecast with appropriately tuned forecasts? Maybe that's especially interesting if you don't know exactly the utility functions of each player. You just know that they're from some polynomially sized type space. Yeah, so that would be a cool. Yeah, so that would be a cool unsolved problem. Yeah.
So let's say that you had some arbitrary type space, or you had some epsilon net over payoff function. We tried to pretend that this was a work based on analysis.
Well, it would be the pretending that it's polynomially sized that would be the trickiest part of the pretending that you're proposing. So it'd be like exponential in m. Yeah, so the epsilon net would be like would be of size, like 1/epsilon to the m. So like, yeah, so like this would work for like a constant dimensional type space. Right, so kinds of things this would work for are, like unit demand auctions, where your type space is, like a number.
Okay, right. So it works fine. Like it doesn't the type space itself is on the side,
That's right. So in general, I mean, okay, it would depend on the details of the setting, but in general, like in a first price auction, by discrete, the type space is real valued. It's maybe values between 0 and 1, but like if you discretize it at epsilon, you'll get an epsilon net in like utility space, like so you need some like Lipschitzness somewhere, but in most games you would have that. That's right. So you can think of what we're doing as an efficient way to coordinate arbitrary numbers of players in who have utility functions from a polynomially sized type space, like a unit demand auction or any other single parameter domain, I suppose, to play a correlated equilibrium without requiring that they have the sophistication to run their own no swap regret algorithms. Okay, good. Other questions? Okay. Okay, so as I've already mentioned, like this will be a relatively direct application of the machinery that we have already developed. The machinery being the ability to make predictions that are conditionally unbiased, subject to a polynomial number of conditioning events. So what I want to do this class is define for you a small collection of conditioning events relevant to a particular decision maker, and prove that if the forecasts have low bias subject to those conditioning events, then the decision maker, if they are best responding to the forecasts, will have low swap regress. And then, we already have the algorithm. Okay. Okay, so let me define the best response events. For a particular decision maker. Okay, so let's fix a state space. C, it's going to be a d-dimensional state space. And an action set A. Okay, so an agent will be defined by their utility function here. So given a utility function U, which is a mapping, remember, from actions across states to numbers, let's say between 0 and 1. Okay, so a utility function tells you as a function of the payoff relevant state and as a function of what you do, how happy you are. For each action, I want to define the best response events. So the best response event corresponding to that action will be the following. I'll write E for event, and it's parameterized by the utility function U and the action. Okay, so it's an event specific to this agent, this utility function U, and read this as the event that agent with utility function U decides to play action A, okay, which is a function of the forecast, is just the indicator that action A is what the agent would play if they best respond with their utility function to the forecast state. Okay, it's just remember the best response function given a utility function to the state is just the function that returns the action that maximizes utility given that state, breaking ties in some consistent way. So let's say you break ties lexicographically. So maybe, if you're indifferent between action 2 and 3 and 9, you play action 2 because it's the earliest one. Okay, so like there could be ties in your expected utility for an action. I just want the best response function to be like a well-defined function. So let's just say you break ties by playing the earliest indexed action. Okay, and then I'll define a collection of events for a let's say, okay, so this is sort of for a single utility function. Okay, you can think of this as, for a single utility function, there's one of these events for every action. Okay, and then maybe we have a bunch of utility functions. So given a collection U of utility functions, I want to define the collection of events, fancy E sub U, to be all of the events we've just defined. So the events that someone with utility function little u takes action A, little a, the collection of one such event for each of the utility functions in your big set U, and also for each of your actions in the action set A. Okay. So does this collection of events make sense? So basically, there, say I have a collection, so we've got a bunch of decision makers who sort of share the same payoff relevant state space and share the same action space. Okay, and now I have a collection of decision makers, each parameterized by a utility function. Okay, I've just defined an event for each utility function cross action. Okay, so the total number of such events I've just defined, since the whole point is going to be efficiency here, the total number of such events is just the product of the number of utility functions times the number of actions, but crucially independent of D. Okay, so the number of, I don't care how high dimensional this state space is. Okay, D does not show up in the number of events here. This is a number of events that depends only on the number of utility functions on the number of actions. And each event corresponds to whether a player with a utility function in this set, given a forecast, thinks that it is a good idea to play action 5 or action 6 or action 7. Yeah. That's right. Yes. So yes, so this is where it's going to be sort of qualitatively different than calibration. So the eventual statement will be that if you tell me a collection of utility functions, then there will be an efficient algorithm, efficient in the number of utility functions that, and D, of course, that causes every agent with utility function in this set to have swap regrets sort of scaling with root T. But you're right that the order of quantifiers here is that first you tell me the utility functions. The reason you need to tell me them first is because I'm going to use them to define these events, and I'm going to run our algorithm for making unbiased predictions subject to arbitrary collection of events. And that algorithm needs to know what the events are. That's right. So like, again, pulling on the string, when you get back to our algorithm for making unbiased predictions, at every step, it's going to have to evaluate expressions like this. Yeah.
One thing, I don't even have to make predictions for this. Okay, I'm giving an ultimate goal of the predictions to the agents that respond and best responding gives them a profit.
Yeah.
So what I would do is, since I know the function, all I need to do and solve the predictions. But I will just based on the state, I do the best response computation myself and make calibrated forecasts for what should be the best response for each of the agents. Maybe
that's a good intuition for like one agent.
But I could still make it multiple. So I could make similar case. You're just taking time for something.
Yeah.
Or just I give like a k log n maximum of that. K log n bit vector. This is in the prediction or like each the support of the okay, you know what? This is going to be the best.
If you were willing to make a separate prediction for each agent. That's right. You could do that. That's right. Yeah, so maybe that's an intuition. You could do that. That's not what we're going to do. We're going to make a single prediction that simultaneously encodes the information. But yes, in principle, you could do that. Okay, but yeah, maybe just to say out loud the intuition. So we've got our state space, and it's like discretized. I'm drawing 2 dimensions here, but in general, this would be like D dimensions. Okay, so you can think of the sort of state space as being some big grid, right? Like each point in the grid is a prediction I could make. In D dimensions, there's a lot of predictions I can make. That's like a problem. But the point, like from the point of view of a single decision maker who is playing best response actions, you know, there's plenty of distinctions in predictions that we must make if we're asking for calibration that are sort of irrelevant for this decision maker because it would cause them to take the same action, right? So like the decision maker, suppose the decision maker has two actions, okay? So then their decision function will be to ask the question, is my utility for playing action 1 greater than or equal to my utility for playing action 2? Well, these decision makers have, their utility functions are linear in the state for each of their actions. So this would be a linear decision rule. And so, there would be some like line through space such that if the prediction is, above the line, then they would play action 1, otherwise they would play action 2. Okay, and calibration would ask for self-consistency, unbiasedness, conditional on playing this grid point, and conditional on playing this grid point, and conditional on playing this grid point, and conditional on playing this grid point. But in some sense, this would be overkill for that decision maker. They just care, are you above the line or are you below the line? Okay, and so here, like there would be only two conditioning events, like you should be unbiased, conditional on predicting something above the line, and you should be unbiased, conditional on predicting something below the line. Now, maybe this intuition, although you could do what Eshwar said and sort of produce a vector equal to the length of the type space, say, and to just encode like the, a suggested action for each player. What we're going to do is we're going to predict a state that everyone can sort of straightforwardly best respond to. Now, maybe the intuition gets like a little bit hairier there because, let's say everyone has, a small number of actions, okay? Their best response regions are defined by, the intersection of a bunch of lines. And okay, now, if I'm also sort of trying to handle a bunch of decision makers and I write, all of their best response regions on here, works better in D dimensions, but I have trouble drawing in D dimensions, then like the number of regions that are like the intersections of all of these linear functions defined by all of their utility functions, that can get quite large. And so you might worry that going down this path, you'd have to handle like all of the intersections of those regions. But somehow like our analysis is going to show that like, yeah.
When going on the path, I think you have to stop looking at the state trees and just take each region independently and try to think of each region as like a log n dimensional. Try to get calibration for log n.
What's log n here?
Log n is sort of the amount of distribution what their action is for the next one.
What's n here?
N is the number of actions, the upper bound and upper usual upper bound, other actions for each one. Each of them, you're just trying to count the number between 1 and n. And all you want is whenever you make a prediction height you make it to some probability form. Yeah, I'm not completely sure, but I think that you can bypass trying to think about the state space in the first place and just think of it as a lower dimensional calibration.
I'd be interested to, maybe explore that. So I understand the intuition for sort of what I think of as like a somewhat orthogonal approach where I'm going to forget about the state space entirely. I'm just going to tell everyone what to do. Like my message to you won't be a prediction of the state, it'll just be an action. And I can just tell everyone separately what to do. But I'm not sure how that intuition carries over when the thing that I'm doing is predicting the state that is, that is going to be payoff relevant, like simultaneously through the best response function.
like it's not really telling you that like you're mostly getting that.
But like, there's a very simple thing. Like if I wanted to do something totally different and just separately suggest actions to people, then that's a very straightforward thing I could do is I could just separately run a no swap regret algorithm for every utility function. And the message I would send is just, if you have utility function, 126, then I suggest you play blue today. That's, the
of the number which is labeling of what the best swap is.
Okay, that I don't totally get, but maybe we can talk about it later. Okay. Okay, but maybe maybe this is a good point to sort of go through the intuition for why unbiasedness subject to these collection of events is enough to give no swap regret to an agent who's treating them straightforwardly. It's trusting them and is best responding to them. Okay, good. So suppose I'm best responding to these predictions. What do we need to show about my sequence of play? Well, we need to show, if I'm going to have no swap regret, that for every pair of actions like A and B, on the subsequence of days on which I played A, I would not have substantially gained by switching to play B instead. If I can argue that for every pair A and B, that means I have no swap regret. Okay. So let's think about the subsequence of rounds for which I played A. Okay. Now remember, like my utility function in the settings we're talking about can differ arbitrarily for different actions, but fixing an action, it's linear in the state space. Okay. So my utility on a subsequence of rounds for which I played a constant action, on a subsequence of rounds for which I'm just playing action A, okay, the average of my utility over these rounds, because my utility function is linear, it is my utility for the average of these rounds. Okay. Now, I'm playing best response. So the subsequence of rounds for which I played A, that's just the subsequence of rounds for which the prediction was such that my best response was A. And so that's one of the subsequences on which the predictions are unbiased. Okay, now I only care for estimating my cumulative utility about the average of the states on this subsequence. And the low bias condition tells me that the average of the predictions on this subsequence was up to whatever my bias term was, equal to the average of the actual outcome. Okay, so there's maybe two different things to keep in your mind. Like at every round, there was the utility I thought I was going to get when I played action A, best responding to the prediction. And then there was the utility that I actually got when I played action A, and I was surprised that the outcome was different than the prediction. And the point is, of course, day by day, the utility I got doesn't have to have much to do with the utility I thought I was going to get. But the bias condition means that on average, over the rounds for which I played A, the utility that I got was equal to the utility I thought I was going to get. Right? Because the only thing that matters for my cumulative or average utility is the average of the states. And the bias condition tells us that averaging over all of the rounds for which my best response was A, the prediction was equal to the outcome. So the cumulative utility that I thought I was going to get if I was trusting the predictions is equal to the cumulative utility I actually got for the real prediction. So if I had closed my eyes at the beginning and didn't look at the day-by-day payoffs and only opened my eyes at the end and just asked, in hindsight, having woken up, what was the average utility that I got, like on the days when I played A, I would have no reason to suspect that the predictions were not totally correct. Okay. Okay. Now, how much? Oh, Natalie. Certainly the best response need not be A day by day. Yeah, good. So we haven't talked about action B yet, too. Action B is going to also be a central character in this argument. So let's think about the utility I would have gotten had I played action B. Okay, that is some other linear utility function. That is some other linear function of the state. Okay, now remember, our predictions are you know, like unbiased in the state space. So right, the whole vector of predictions is unbiased on the subsequence of days for which those predictions caused me to want to take action A. Okay, so on this subsequence, I can also estimate what I think my utility should be if I play B, and what my utility actually is if I play B. And again, like round by round, those could wildly differ. But as averaged over the whole subsequence of rounds for which the predictions made me want to play A, my expectation, given the predictions, for how well I would have done had I played B, that's equal, up to the bias terms, to how well I actually would have done had I played B. Okay, so I can estimate how well I think I would do if I played A, and how well I actually do if I play A. I can estimate how well I think I do if I play B, and how well I actually do if I play B. And the bias condition is going to say, as averaged over the sequence for which I played A, my expectation, like how well I think I'm going to do if I trust the predictions, is equal to how well I actually do, both for action A and for action B. Unbiased. Or I don't know what you mean.
Sure.
I want to be unbiased on n different things. Conditional on the prediction causing me to want to play action 1, conditional on the prediction causing me to want to play action 2, and so on. Okay, and yeah, and so just to be clear, what that's going to give me relevantly here is that if I look back on the subsequence for which I played action A or B or C or D, it means that not just for that action, but for any other action, my expectation or my prediction on average for what the payoff would have been had I played any of those actions is equal to what the payoff really was on that subsequence for those actions. Okay, so I'm able to correctly estimate, at least in this average sense, not just my payoff for the action I actually took, but my payoff for any counterfactual action. Okay, so long as the subsequence is such that I'm playing a constant action throughout the subsequence. Okay. Okay. So what have we argued so far? Like my payoff for playing action A on average over this subsequence was what I thought it was going to be. My payoff for playing action B over this subsequence, it was what I thought it was going to be. But what is the subsequence? It's the subsequence of rounds for which my best response was A. Why did I play action A instead of action B on this entire subsequence? It was because point-wise, day by day, the predictions were such that my payoff for action A was higher than my payoff for action B. Action A was a best response to the predictions. And so if every day my predicted payoff for action A was only higher than my predicted payoff for action B, and also my average predicted payoff for action A was equal to my average actual payoff for action A, and my average predicted payoff for action B was equal to my actual payoff for action B, well, then it must be that my average actual payoff for action A was higher than my average actual payoff for action B, and hence I don't regret not having swapped B for A. That's the intuition and almost a complete proof. That's what we're going to formalize. Yeah.
Thing that you're at, right? So is this?
What do you mean the thing that the thing I'm providing is just a guess of the state. And remember, there's not one person I'm recommending for. Eventually, I'm going to do this with a bunch of downstream agents in mind. My running time will depend on yes, on the number of downstream agents.
Oh, and the reference form.
And the regret bound will depend on this as well, but only logarithmically. That's right.
Again, can clarify you're saying that once you fix the action, the utility is negative the state. But in reality, the state is good because unbiasedness.
Because then the average of the utilities over the states is equal to the utility of the average of the states.
That's for this, the utility of state is transferred over to subsequent from the state of the action, and say that measuring the utility of the solution is pretty much the same as the utility of the state. And therefore, one of the response, action A is the best response for the predicted action is also pretty much the best response for the two. That is the
Or it's not, yeah, like action A is a best response like round by round for the predictions. It's not a best response round by round for the true states, but like it is a best response if you have to pick a single action over the sequence. Right. So like there's your expectation for how well you're going to do for each action, and then there's the real thing. And the unbiasedness means that, you know, in general, like how well you think you're going to do is different from how well you would actually do, but they're roughly the same as averaged over the sequences on which these events are active, and those are the sequences for which your best response function tells you to play each of the actions. Right, so that's what translates pointwise optimality of the best response function under the predicted states to just a swap regret bound under the real states.
Very different one that if all they had was the algorithm the last time we got the class, that is effectively I can use the black box of the algorithm.
That's right. And like if all you wanted was an algorithm for one player to get root T swap regret, you could just use the algorithm from 2 lectures ago instantiated with these events. In fact, the claim is you could do it for a bunch of agents at the same time. But like, yeah, like you could just, like this would also be a way to just derive an algorithm. In fact, like next class, we'll do that for subsequence regret for like very large action space games for which we previously didn't have an algorithm. Okay. But yeah, good. So you can think of these as coordination mechanisms. Maybe for swap regret, since we already have no swap regret algorithms, that's the natural way to think about them. Now you could also think about them as, you could also think about this as just an algorithm design principle, right? Like if I can give you a no swap regret algorithm by like, or if you get no swap regret by just best responding to like appropriately unbiased forecasts, then okay, one way to design a no swap regret algorithm is to make appropriately unbiased forecasts and then best respond to them. Now it would be sort of a roundabout way to do it in this case because we already have no swap regret algorithms. But yeah, for like online combinatorial optimization problems, which we'll talk about, you know, next class, we previously didn't have efficient algorithms to get like subsequence regret, like the subsequence regret algorithms we've derived already in this class have running time that scales polynomially in the number of actions. Because they have to write down this matrix that sort of scales with the number of actions and computes an eigenvector of this matrix. Even though like there's some lower dimensional representation of like the utility functions, right? So like online shortest paths problems. You know, the subsequence regret algorithms we had already didn't take advantage of that lower dimensional structure, and this kind of machinery will give us the ability to do that. And there's, although you could also think about it as a coordination mechanism, like it's also interesting to think about this as an algorithm design paradigm there because we didn't have algorithms before even for a single agent. So like you're asking like if this is like a game, what's going on? Yes. So like in general, the state could be a function of everyone's action. So like in a, like we'll talk about, you know, online shortest paths next time, which is, you know, naturally viewed as a game. There, the state is like the congestion along each of the roads, if there's, you know, like D roads. But of course, the congestion is a function of the actions chosen by every player. the nice thing here, the nice thing about this framework, right? Like we're showing how to make low bias predictions and therefore have you know, as we'll show in a moment, no swap regret for all of these downstream agents for adversarially chosen sequences of states. So in particular, like if you had a process that generated states in some non-arbitrary way, but you know, some particular way, like looks at what everyone's doing and writes down the congestion, it applies there as well. Okay, there's a slight caveat of needing to separately randomize for each agent so that, you know, because remember when we derive these algorithms, like the learner has to choose a distribution over actions and the adversary can know the history, but not the actual randomness of the learner. So if, you know, if the actions depend on our predictions, then there's the slight caveat that you need to separately randomize for every player. But modulo that, this all applies to games where the state can depend on the actions. Good. Okay. Other questions? Yes.
If I were to use the same random set out like calibrated prediction about the state to a bunch of agents whose actions influence like the true state,
Yeah.
this can lead to like sometimes lead to the disasters where like it breaks the properties that
That's right. You run into yeah, like it, you know, then the forecasts might not be calibrated anymore because in like the model in which we proved the forecasts would be calibrated was one in which every day the learner picks a distribution of her forecasts, the adversary picks an outcome, and then the learner samples from this distribution. And so the adversary's outcome is not allowed to be a function of the coins used to sample. Now here you have to be a little careful because when we make a forecast and broadcast it, that's actually a sample from the learner's distribution. And if the players are best responding to that sample rather than the distribution, then their best responses are used to form the state, then the adversary, you know, the adversary we have designed is using the learner's coins, which is not allowed in the theoretical framework.
sample, or you sending out samples to fresh samples to make sure
That's right. So the easiest fix to this is to just send a, you know, like when you, what is the hard problem anyway? You solve this minimax problem with, you follow the perturbator, right? That's the hard computational thing. That gives you a distribution. You only have to solve the hard problem once, but you do need to, sample independently for every. Yeah, that's right. But the each individual person is responding to a realization of the coin flips, but the state, the relevant state from their perspective is a function of what other people do. And what other people do is independent of what they did because other people got different samples from them. That's right. But anyways, this is something you'd have to be a little careful about. Okay, yeah.
Final point is that you mentioned it. It seems like it could be a double-edged sword that your coded out and go back, but also be the coordinate.
That's right. Yeah, I think there are good, interesting questions about, yeah, like to the extent that you can really use this as a correlating device in the classical sense, because I mean, okay, in a correlating device in general, not everyone sees the same signal. That's okay. But yeah, it would be nice if there was a version of this where everyone saw the same signal. And I think there's some interesting questions there. Okay. All right. So what's the claim? So let's fix a set of utility functions U over some state space C, such that each utility function, which recall is a mapping from actions cross state space to numbers between 0 and 1. Okay, we're going to assume each of these, as usual, is linear and L Lipschitz in its second argument, so in the state. Now let's fix a transcript of predictions. Or we're predicting the states. So predictions, let's call them S hat 1 through S hat T. That has bias alpha. Conditional on the events we just defined. So these events, E sub U. Okay. Suppose an agent who has utility function in this set every day just trusts our predictions and best responds to them. So it takes an action AT, which is a best response to our predicted state. Okay. Then that agent has bounded swap regret. So in particular, if I look at swap regret, so the maximum over all swap rules, mapping actions to actions of the regret to that swap rule in hindsight. So the sum over all of the rounds of see if I need to carry this expectation everywhere or not. Let's try not writing expectations. The sum over all of the rounds of the utility they would have gotten had they applied the swap rule to their action at day t, given the actual realized state at day t, minus the utility they actually got, playing action t, given the realized state. Okay, so this is the swap regret. But this is bounded by 2 times the number of actions times alpha times the Lipschitz constant. Okay, so instead of saying, I mean, think of the Lipschitz constant generally as being like 1, right? Like if what I'm predicting is discrete outcomes and what you care about is your expected utility, the Lipschitz constant is going to be 1. Okay, so this is saying like, you know, if I can get bias on these events alpha, then your swap regret will also scale by alpha. It'll be bigger by a factor of the number of actions. If we were more careful, we could get it to be bigger by a factor of square root the number of actions. Exactly. The theorem is really that you'll get internal regret alpha, and then the factor of the number of actions is the conversion from internal to swap. Okay, so this is the theorem. And remember, we can get alpha to be something on the order of root t log d. Okay, so you know, this is going to give us like the same swap regret bound as we got with sort of our bespoke algorithm, up to an additional factor of log of the number of utility functions. So what we're paying in order to make predictions useful for a whole collection of utility functions is a like to say logarithmic term in the regret for the number of utility functions. Okay, this is the theorem. That's right. It's like what you pay for is log of the number of events. So it's log utility functions times actions. So yeah, it's like log number of utility functions plus log number of actions. Yeah, exactly. You're paying very, very little for these predictions being simultaneously useful for everybody. Okay. Good. Yeah, maybe one, like you had sort of proposed, like a simpler thing you could do is I could just run a swap regret algorithm for, each utility function in U, and like just that the thing I send is, this says if you have utility function 1, play action, red. If you have utility function 2. This would result in sort of a scheme that had much higher communication complexity. Like I would every day have to publish a vector of length equal to the number of utility functions. So the length of the vector I'm publishing would scale with the number of utility functions. Whereas that doesn't happen here. Like I'm just publishing something that looks like a state independently of the number of utility functions. Yeah, and in fact, in the routing example, it wouldn't work at all because I don't have a different algorithm to get no subsequence regret, like an efficient algorithm to get no subsequence regret for routing games in the first place. Okay, so let's prove the theorem. Okay. Okay, so like a useful lemma, I guess, is almost immediate, but worth noting. Is the following. Let's fix any two states. S1, S2, these are both d-dimensional vectors. And also any two constants, C1, C2, these are, let's say, non-negative real numbers. Suppose that A is a best response, it's the best response to S1, and A is also the best response to S2. Then A is also the best response to CS1, C1 S1 plus C2 S2. Okay, so sort of saying like the best response correspondence is like convex. If I have, two states for which A is the best action, then any, non-negative linear combination of these states, A is still a good action. Okay, and this is almost immediate from the definition. Right, so, let's consider some other action A prime not equal to A. Okay, so like what I want to look at is the difference in utility between playing action A and A prime. If A is the best response, it should be like only positive. If it's not the best response, it should be negative. And so let's look at the difference in utility of playing action A when the state is C1 S1 plus C2 S2 compared to, the utility of playing A prime when the state is C1 S1 plus C2 S2. Okay. Okay, now the utility functions for every fixed action A and also for every fixed action A prime, they're linear in the state. Okay, so we can, this is a linear combination of states. We can like take the linear combination outside the utility functions and write this as C1 times the difference in utility for playing action A when the state is S1 and playing action A prime when the state is S1 plus C2 times the difference in utility for playing action A when the state is S2 and playing action A prime when the state is S2. Okay, and remember A is a best response when the state is S1 and it's a best response when the state is S2. So both of these terms are positive, so the whole thing is positive, and so A is still a best response. Okay, so this is going to be like a useful fact that if I have a sequence of states for which A is a best response, and now I'm considering what I should do for some non-negative linear combination of the states in that sequence, the answer is still A. Okay. Okay. Okay, so let's prove the theorem. So the theorem says something for every utility function in this set, and well, instead of writing this as the max over swap functions, I could write this as for all swap functions. Okay, so it says for every utility function in U and for every swap function phi. We need to prove something for each of those. So let's fix any utility function in U and let's fix any swap function and show that for that utility function and that swap function, this theorem holds. Okay. So I've got, let's look first at my utility for just naively trusting the predictions and best responding to them. Okay, I want to show that this is big compared to any swap I could apply. So what's my utility for being naive and trusting the predictions? Well, it's the sum over all time of the utility that I get when I play the action that I play when I trust the predictions and best respond to them. But, you know, like it's not the utility that I would get given the predicted state, it's the utility I get given the real state. Okay. Now, this is the sum over time, but I'm playing different actions at different time steps. So I can, I can sort of decompose this. I can just pay attention to which actions I play when. Okay. So one way I could write this is as the sum over all of the time steps of the sum over all of the actions of the indicator that I played action A times the utility function that I get, times the utility that I get, you know, given that I play action A. Okay, this is just an obfuscated way of writing this because, you know, this sum will have exactly one non-zero term, the one corresponding to the action that I actually played. Okay. And now I want to do two things. So first, I want to note that this indicator function that I play action A, this is exactly one of the events that I'm conditioning on because action A is what I get out of best responding to the state. Okay, so I'm explicitly conditioning on someone with utility function U deciding at some round to play action A. Okay. And the other thing I want to do is I want to take advantage of the linearity of the utility functions and bring this sum over time, which is right now happening outside of the utility functions, inside of the utility functions. Okay, I'm allowed to, when am I allowed to do that, by the way? I'm allowed to do that for any sequence for which the action is fixed, right? Because the utility functions for every action are linear in the sequence. Of course, they could be totally different for every fixed action, the utility function is linear in the state. Of course, there's no relationship between the utility function for different actions. So if I want to bring a sum of states inside of the utility function, I have to make sure I'm doing so only on sequences for which the action is fixed. Okay, so let's try to arrange for that to happen. So first, I want to sum over time steps for which the action is fixed. The first thing I want to do is interchange these two summations. I want to sum over actions on the outside and time steps on the inside. Okay, so this is the sum over all of the actions. Okay. And it's the sum over all of the actions of the utility that I get for playing action A. Okay, so fixed action. And all of this stuff that sort of I'm summing up here, right? Right now outside of the utility function, I'm going to bring that inside of the utility function, but that's okay because fixing an action A, the utility function is linear. Okay, so it's the utility I get for playing action A when what's the state? When the state is the sum over all of the time steps of the event that I played action A. Remember, what's a different way to write that event? Well, we had a name for it. It's the event parameterized by utility function U and action A. It's a function of our prediction at time step t. This was just our name for this event. Times the state. Okay, so I've interchanged these summations. The indicator function was like outside here. And then, you know, like once an action is fixed, I can, by the linearity of the utility function in the state, can bring the sum over time inside. Okay. Now, this is exactly a sequence on which our forecasts are unbiased. What does that mean? Well, it means that up to error alpha in each coordinate, I can replace this sequence of actual states with sequence of forecasts, right? Like what bias meant was that the sum of the states times the indicator function for the events, this thing, of the forecasts was equal to the same sum of the states. Okay, so I have the states here. I can replace them with the forecasts up to this bias term alpha in every coordinate. Okay, so this bias term alpha in every coordinate is going to cost me something, but not too much because the utility function is Lipschitz, L Lipschitz, so in the L infinity norm. So this bias alpha in every coordinate is going to cost me alpha L. Okay, so this is at least the sum over all of the actions of the utility that I get for playing action A when the state is the sum over all of the time steps of this event defined in terms of my prediction times not the real state, but my predicted state. Okay, here I'm using the bias condition, and that costs me in each one of these terms alpha L, because the bias wasn't 0, it was alpha, and that could hurt me by as much as alpha L because my utility function is L Lipschitz. Okay, but what is this? Well, this is the utility for playing action A against a linear combination of predictions. And the way I chose the action was by best responding to the predictions. So I know that my action was since my action was a best response to each of these predictions, and we just proved this lemma, I know that action A for this average of predictions, it's not just, but like this is a best response. Okay, so this gives me higher utility than any other action I could have played. In particular, higher utility than phi of A, which is just some other action. Okay, here I'm using the fact that, right, so just, morally what's going on, I use the bias condition to translate from the real outcomes to the predictions. Okay, and now I know a lot because the agent here was best responding to the predictions, and best responding is a really good idea. Okay, so by the best response condition, this is at least as large as the utility that the agent could get for any other action, in particular for action phi of A, is just some other action, if the state sequence was the same. Okay, and let's just deal with this term as well. We're losing alpha L here in each term of this sum. How many terms are there in the sum? Well, there's one for each action. So this, what I've lost here overall is alpha times L times the number of actions. Okay. Now we're not quite done yet, because this is talking about my utility if I played some other action on this state sequence, but this isn't the state sequence, this is the predicted state sequence. Okay, but like I can do everything in reverse. So basically, right, like what's happening, the bias condition had me move from real state space to predicted state space. The best response condition said in predicted state space, I can't have done better by applying the swap function because the best response was pointwise optimal. And then the bias condition again is going to allow me to move from predicted state space back to real state space just by losing another factor of alpha L times A. Okay, right, like the same, but like everything can happen in reverse again now that I've, right, like, yeah, everything can happen in reverse again now because, it's the same sequence. I've switched actions now. The utility function is, again, fixing this action linear. Okay, so I just apply the bias condition again for this other utility function. Now it's got a different action plugged in. I can go back to the real states, losing an alpha L term for each action. And again, because this phi function, it's mapping actions to actions on any sequence for which the action played, for which the action A is constant, phi of A is also constant. And utility functions are linear in the state given a fixed action. And so I'll again be able to move the average over states inside the utility function to an average over utility functions on the outside.
For the first time value from n to n hat, and the second time value from n hat to
it's the same conditioning event. Well, I do need, like, okay, so I'm just using the same conditioning event to go from S hat to S, but then the next step is going to be, right, I've got the utility function where the state is the sum over time, and what I want is the sum over time of the utility function of the state. For that, I need the utility function to be linear, and the utility function is only linear conditioned on the action.
So this is the same conditioning event,
it's using the linearity of the function fixing A, and I'm using the fact that fixing A fixes phi of A. If I was using a comparator class that was not constant conditional on this conditioning event, I would run into trouble. Okay, let me finish this up real quick then. Okay, well, you can just do, yeah, let me get to the question. That sounds more interesting. So let me just skip all the rest of the steps. And, you just do all of this backwards again. It's greater than or equal to the sum over all time of the utility of phi of AT when the state is the actual realized state, ST, and you've done the trick twice, so you've paid the penalty twice, 2 alpha A times L. And let me just remember what our bound on alpha is, right? If you use our algorithm for making unbiased predictions, the bound, well, first of all, the algorithm runs in time polynomial in D and the number of utility functions and the action space. And the bound you get is, the swap rate bound you get is 2 times the number of action space, the number of actions times L times, okay, the bias term, which is root T times log of D times the utility function, number of utility functions times the size of the action space, all of this inside the log. This is the same thing we got from the sort of bespoke algorithm for a single player, except we didn't have the log U term. Okay, that's the theorem. Okay, what was the question?
That seems more like something I than probably about the calibration. You're making randomized forecast.
That's right. So the algorithm, if you remember, every round it's solving for a minimax equilibrium, which is a distribution over forecasts and sampling from it.
So I guess there are no and it seems to me that the calibration guarantee
That's right. That's right. So in the notes there are expectations. I just didn't want to write them over and over. But basically, yeah. But like what this is sort of saying is if the realized bias is alpha, the realized swap regret is that. Now for a fixed realization of the forecasts, notice the learner is also playing a deterministic algorithm. They're just best responding to them. Now we know that deterministic algorithms can't get no regret. So what's going on? Well, we don't have an algorithm that guarantees with probability 1 the realized sequence has this bias. That would be it's not a deterministic algorithm. What we have is a randomized algorithm for making forecasts that guarantees that the expected bias is alpha. And so, and fortunately, yeah, like because the utility function is linear, the expectations behave the way you would want. And so what you get in the end is an algorithm that has expected swap regret. This.
Everything you've written here is perfectly true. You just take the fix the realization of prediction. If the calibration error was alpha, whatever it is, if on a sequence basis it might be larger, but you don't care about it.
That's right.
Then this error is the swap regret of whatever is chosen.
Yes.
And now it's the expectation over the swap regret overall.
Exactly.
Your expectation over the alpha. Well,
that's exactly right. Exactly. So this is if you have a transcript in front of me that has realized bias alpha on these events, then I can just tell you that the agent has realized swap regret at most this, but our algorithm for producing forecasts promises something about the expected bias, and like something like that. There has to be some randomization somewhere, right? And the agent here is not randomizing. The agent is just deterministically best responding to the forecasts. So it had better be, for this to lead to any kind of algorithm, that the forecasts are randomized, and indeed they are.
Before you said this, I consider that just because you're best responding to the sample doesn't mean that you will do the same thing. They take expectations for the forecast. Yeah, I guess I'm sort of trying to take the wrong stage. Where do the analysis because your actions themselves that you control are random variables.
The actions are deterministic functions of the forecasts, but because the forecasts are random variables, the actions are also random variables.
Yeah, but
that's right. But yeah, like you can, basically you can put expectations around this. Okay, this becomes a probability now. this becomes an expectation in here. That is the thing we proved the bias about.
Again, today I was the balance at the end towards the sequence, but the thing that it was no atomic version of the value.
You just take expectations over, you can take the expectations round by round. So the theorem we proved about the bias of our predictions was about the expected bias of the predictions, and the analysis was round by round. Yeah, cool, okay. All right, see you guys on Wednesday.